Here is a problem about radioactive decay. Okay, well, let's take a look at the nice formula that we're going to use first. The amount of radioactive element A at the time t is given by, here is our nice formula, and we can take a look at this and we can say to ourselves, boy, that sure does look similar to continuous compound interest, where that would be principal, that's a rate, and t is time again. And if you thought that, well, you're right, it looks pretty much exactly the same. And we're even going to say that these are the same things, right? A sub 0, this is the initial amount of the element. So that's still an initial amount. So really we're doing the same exact thing. But our K value is going to be bigger than, or excuse me, smaller than 0. In the interest problems, usually our K was bigger than 0 because we wanted to gain money, right? Our interest got bigger and bigger. So our number here was larger than 0. But here it's going to be smaller than 0 because we're going to see how much time it takes for the radioactive element to decay, not to grow. All right, so this is just what this is called, the constant of proportionality. So, I mean, we can just think about this constant of proportionality to be similar to rate when we're talking about continuous compound interest. Okay, so essentially we got the same nice formula we had for continuous compound interest, but it's just a little bit in a different setting, right? We're not talking about money. We're talking about decay of an element. Okay, so let's do it. So we've got cobalt-60 has a half-life of 5.27 years. So what this means is that if I have a certain amount of this element, cobalt-60, and I wait for 5.27 years, half of it will have decayed. So I will only have half of the amount that I started with after 5.27 years, right? Okay, so we want to find the constant of proportionality K. So if we're just strictly thinking about this in terms of the nice formula, we can do this the way we did those last problems with continuous compound interest. We can just, identify what the variables are. So where are we? Cobalt-60 has a half-life of 5.27 years. Find the constant of proportionality K. So we want to know what K is. We do know that half of our cobalt-60 will be left after 5.27 years. So we could say that the amount, if we called the initial amount 100%, that's just 1, then our amount that we finish out with is going to be 50%, right? Or we could write 0.5. Okay, so we've got that, we've got that. K is the piece that we don't know. And T is, well, 5.27 years. Okay, so now that we have these arranged, we can say that A of 5.27 would have to be 0.5. And that has to be, we're just, plugging it into the nice formula here, right? A of t, we put 5.27 here. Our initial amount now, this is 1. And then we've got e to the k times t power, so 5.27 times k. And now we know that this relationship has to be true. So if cobalt-60 does have a half-life of 5.27 years, then this is mathematically what that's saying. So we can take this guy and just solve for K. And we can do that pretty quickly in the same way that we did solved equations involving exponents. So we can just take this and we can either rewrite it with logarithms, or what might be simpler for us to think about is just applying that logarithm to both sides. And now we can use that power rule, right? So we've got natural log of 0.5 is the same as 5.27k times natural log of e. Okay, we know that the natural log of e is just 1, so that just goes away. And we can find k here. This is equal to natural log of half divided by 5.27. Okay, now the system, the computer on WebAssign is going to ask you to round this to some figures. On the one that I looked at, it asked to round it to 6 figures. So this one rounded to 6 figures is that. So here's our K value rounded to 6 figures. Okay, so that was part 1. Done. Find a function that gives the amount of cobalt-60 that remains after T years. Okay, well, we're just going to do the same thing again, but now we're not going to have a T, right? So our 2, we can just write this right away, right? A of T is equal to the original amount, which is 1, times E raised to that power K, so negative 0.131527 times T. And that's it. So after T years, this is the percentage of cobalt-90 that will remain. We could write this without the 1, and that might be more convenient for us. I don't know, I'll just do that. Okay, so there is our nice function that gives us the amount of cobalt-90 after any number of years. Okay, and we're going to use this for the third part. How long does it take for 90% of the element to decay? All right, so how are we going to do this? So if we want 90% of the element to decay, how can we use this? This is how much of the element is left, right? So A of T, this is the amount of the element left after T years. So if we want 90% of it to decay, how much is going to be left? Well, that's going to be 10%, right? If we have 90 of it decay, 10% is left. So we want to solve A of T equal 0.1, right? 10%. So solve for T. That's number 3. All right, so we can do this, right? We just want to know how much time it takes for there to only be 1/10 of the element left, or 10%. So we can do that. We'll just take our nice function that we wrote in part 2, which is right here. And we're going to set it equal to 0.1, and we're going to solve this for T in the usual way. We can apply a natural log to both sides. So now this becomes negative 0.131527 T times natural log of E, which we also know is 1, equals the natural log of 1/10. And now we're home free, because that's just 1. So we have that T is equal to natural log of 0.1 over negative 0.131527. And we can crank that value through the calculator. And I did this ahead of time, right? We can crank that through the calculator, and we can get that that's 17.507 years. Now I rounded that to the nearest third decimal place. Now, depending on what it asks for in WebAssign, you might want to type something else. Maybe it might want it in years and months, or maybe it wants it, rounded to the 10th. I'm not exactly sure, but we can surely round, and I don't think that that's the issue here.